This continues the lecture on Galilean relativity. At the end of the last part of the lecture, I gave you a conceptual example involving two cars moving in opposite directions on the freeway, each moving at a speed of 60 miles per hour relative to the ground. In just a few moments, I'm going to turn that example into my first quantitative problem. Before I do, however, I neglected to actually give you a simpler conceptual example to wrap your head around first at the end of the last lecture. Let me do so here. For example, once again, we're concerned with the following velocity transformation equation. V equals V prime plus U. As I mentioned, you are already familiar with how this expression works because you see it around you in the everyday world. So consider the following conceptual example here before we get to this first quantitative problem. Let's say, for example, that you are standing on the side of a road. You're a stationary reference frame. And then let's say that I'm in a car that's moving towards you at 50 miles per hour. And then I've got this marker in my hand, for example, like so. And then while I'm in the car, I throw the marker towards you like so. Let's say that the marker can leave my hand relative to myself at 10 miles per hour. So then therefore, if I'm moving towards you at 50 miles per hour and the marker leaves my hand at 10 miles per hour relative to me, with what velocity do you see the marker at? 60 miles per hour. You just did V equals V prime plus U, because here's how the expression works. This right here is the velocity of the marker, the object relative to me, the moving reference frame, 10 miles per hour. This right here is the velocity of the moving reference frame, me, relative to you, the stationary reference frame. That's 50 miles per hour. So then therefore 10 plus 50 is equal to 60 miles per hour. This right here is the velocity of the marker relative to you, the stationary reference frame. Okay, here's another simple conceptual example, once again involving this car. Let's say in this case that I'm moving away from you at 50 miles per hour. And then as I'm moving away from you, I turn towards you and I take the marker and I throw it towards you once again, such that according to me, it leaves my hand at 10 miles per hour. So then therefore, if I'm going in that direction at 50 miles per hour relative to you, and I throw the marker in this direction such that it leaves my hand relative to me at 10 miles per hour, with what velocity do you see the marker at? Negative 40 miles per hour. Once again, this is V equals V prime plus U. This is the velocity of the marker relative to me inside the car, 10 miles per hour. This is the velocity of me relative to you, negative 50 miles per hour, because I'm moving away from you. So then 10 minus 50 is equal to negative 40 miles per hour. That's the velocity of the marker relative to you. So you see the marker moving away from you at 40 miles per hour. Now, if you're having trouble picturing this, how could I throw the marker towards you, yet you still see it move away from you? We'll just consider the following simple demonstration. What I'm going to do in just a moment is very rapidly walk backwards in this direction. And as I do, I'm going to take the marker, and then according to me, I'm going to throw the marker ahead of me like so. However, if I move quickly enough in this direction, what you will actually see is the marker fall in this direction like so. This is a rather silly demonstration, but let me go ahead and show it to you nonetheless. Like so. So I threw the marker in this direction relative to me, however, you saw the marker fall in this direction like so, relative to you. Okay, now let's go ahead and take a look at the first quantitative problem. Copy it down from the lecture examples, copy it down into your notes. Let me read it to you here. Two cars are traveling at 60 miles per hour with respect to the ground, but in opposite directions. What is the velocity of one car with respect to the other? So this is now our quantitative problem of the conceptual example that I stated at the end of part 1 of this lecture. Okay, let me go ahead and set this up. Here's the velocity transform. Okay, a problem in Galilean relativity always begins by identifying everything. Because we're talking about motion near the surface of the Earth, for the most part, in fact, without exception, for all of our examples, we're always going to consider the surface of the Earth to be the stationary reference frame, O. So O is the ground. Okay, and then we have our two cars. So let's say that right here is car number 1, and then relative to the ground, it's moving in this direction at 60 miles per hour. And then here's car number 2 moving in the opposite direction, relative to the ground moving in this direction at 60 miles per hour. Which car is the object and which car is the stationary reference frame depends upon how you define things. So let's think of it in the following way. Let's say that we're observers here inside of car number 1 and we're looking at car number 2. If we think of it like that, then basically the question that we're asking is the following. What is the velocity of number 2 with respect to number 1? In other words, if we think of ourselves in car number 1 as observers, what we're saying is that we're moving observers. In other words, car number 1 is O prime by definition, and then therefore the object is car number 2. Notice how that matches up here with how I'm phrasing the problem. What is the velocity of the object, car number 2, with respect to the moving reference frame, car number 1? So then therefore O prime is car number 1, and the object is car number 2. Okay, and then in the velocity transform, we're given 2 of the velocity vectors and we have to find the third. So then therefore, which velocity vector is which? And incidentally, by the way, because this is a one-dimensional problem, I'm going to go ahead and drop the vector notation here and just write the velocity transform as v equals v prime plus u. We'll take care of the directions with positive signs and negative signs in just a few moments. But let's go ahead and take a look at this 60 miles per hour right here. This 60 miles per hour is describing the velocity of car number 1, the moving reference frame, with respect to the ground, the stationary reference frame. So this is describing the velocity of O prime with respect to O. By definition, that's the velocity vector u. Okay, the velocity vector u is a positive number because it points to the right-hand side here on my diagram. Okay, and then secondly, we have this velocity right here. It points to the left, so we'll have to make it negative in just a moment. But before I do, let's see if we can figure out which vector it is. Okay, this 60 miles per hour in this direction is describing the velocity of car number 2, that's the object, with respect to the ground, that's the stationary reference frame. So then therefore, that's describing the velocity vector v. The velocity vector v is describing the velocity of the object with respect to the stationary reference frame. So v is equal to 60 miles per hour in magnitude. However, because it points to the left-hand side on the diagram, therefore we have to make it negative. Okay, and now we just add things up, and then what we're solving for here in the expression is v prime. That is the velocity of the object, car number 2, with respect to the moving reference frame, car number 1. So we have right here negative 60 is equal to v prime plus u plus positive 60. Move the 60 here to the other side of the expression, and v prime is equal to negative 120 miles per hour. In other words, if you're in car number 1 and you look at car number 2, you see car number 2 moving towards you at 120 miles per hour, but the vector itself points to the left-hand side, hence the negative sign. Okay, now the Galilean transformation does, of course, obey the tail-to-tip method of vector addition. So what do the vectors look like in this situation? They look like the following. Okay, first of all, we have v prime. We have this large vector that points to the left-hand side with a magnitude of 120 miles per hour. That looks like this. Okay, and then using the tail-to-tip method of vector addition, we're adding to it u. That's this velocity vector here. This is 60 miles per hour to the right-hand side. So I'm going to place the tail here of this vector at the tip of the first. That then looks like this. So here's u. And then lastly, we have the resultant v. The resultant v is this velocity vector here. This is the velocity of the object, car number 2, with respect to the ground, the stationary observer. That then looks like this. So here's then how you pantomime the vectors using the tail-to-tip method. That is, you have v prime plus u is equal to v, like so. So once again, for this one-dimensional case, conceptually, you're already familiar with the Galilean transformation because you see it around you all the time. However, in the one-dimensional case, adding up the vectors, once you've identified everything, is easy to do. In the next portion of the lecture, I'll begin to take you through two-dimensional examples.